Dr. Tian Zhong, whom I had the opportunity to meet this April in Chicago. His research is really astonishing, and I'm very glad that Dr. Tian Zhong accepted our invitation for this keynote lecture. I'm going to present Dr. Tian Zhong. His research focuses on developing enabling nanophotonic and molecular technologies for building an efficient global-scale quantum internet. In the past decade, Professor Zhong's work has contributed to significant progress in nanoscale quantum network nodes and high-throughput quantum communications links interconnecting distant nodes. His efforts from atomic molecular physics and photonics aspects converge to a vision to advance state-of-the-art quantum information technologies to bring quantum internet one step closer to reality. Professor Zhong has pioneered the field of rare earth quantum nanophotonics. Rare earth ion drop crystals are attractive quantum materials with exceptional coherence properties. By leveraging the modern photonic technologies, he has developed a versatile rare earth nanophotonic platform that could enable scalable quantum optical networks. Professor Zhong was a postdoctoral fellow in the Institute of Quantum Information and Matter and the Department of Applied Physics and Material Science at the California Institute of Technology. He completed his PhD in electrical engineering at the Massachusetts Institute of Technology in 2013. Before his PhD, he obtained his Master's of Science degree at MIT in 2009 and finished his undergraduate studies at Nanyang Technological University in Singapore in 2007. Professor Tian, thank you very much for agreeing to be here, and please, you can start whenever you want. Thank you.
All right. Hi, everyone. Welcome to this lecture, and thank you, Boris, for this very kind introduction. So today, I would like to take probably 40 to 50 minutes of your time and to give you this high-level overview of this particular interesting quantum technology called quantum communication networks. Okay, my plan for this lecture is, first, I would like to walk you through a brief history about a quantum entanglement, which is a bizarre phenomenon or amazing phenomenon that happening in quantum physics that eventually led to the discovery of a variety of kind of quantum technologies that we're talking today. And then I will briefly talk about how to utilize quantum entanglement to enabling some useful technologies such as quantum cryptography, and more interestingly, hopefully, a specific example of using quantum teleportations to transfer information. And at the end, if I still have time, I would like to give you an update about the state of art and what's going on around the globe to build a so-called quantum network, where is a new technology, is a quantum version of the internet that we use today to have this Zoom calls, but will offer a lot more exciting opportunities to enable not only faster, quicker, but also a safer and secure communication networks. So to start off, I would like to start with a very quick overview of the history about this very important, but also very weird phenomenon called quantum entanglement. In the early 20th centuries, where a group of scientists start to struggle with a hypothetical concept or thought experiments, where we gather together two quantum particles. In this specific example, I'm using electrons as a quantum particle. Electrons, as you may know, that is a particle that actually spins by itself. So depending on the orientation or direction of the spin directions, the electron spin can be in two possible orientations, either a spin up or either a spin down. So this is indicated by the red arrows that I'm showing in this graph. And the electron spin can be both in spin up state or spin down state. And roughly speaking, it can happen at the 50% each scenarios. Now imagine we have two of these electron spins and we put them together in a specific way such that we call them a shared entangled states. So mathematically, or maybe before I introduce the mathematical formula, the entangled state of these two particles basically says that if the first spin is in spin up state, or the arrow spinning up, then the second spin is always in spin down. So it's always in the opposite spin. And vice versa, if the first spin is a spin down, the second spin is always a spin up. So they always come up in the opposite states with respect to each other. Now, mathematically, this quantum entangled states, it can be written in this formula. And this will be the first formula I show you in this slides. And I promise I only show you 3 formulas in this talk. So don't be bothered by the too many mathematics, which I won't do in this lecture. So in this formula, the first term indicates if the first spin is measured in the spin up direction, the second spin is guaranteed to be in spin down direction. And likewise, there's other possibility where the first particle is spin down and the second particle is spin up. In quantum physics, since we're in a situation we don't know which scenario it is, there's a 50% we're measuring the first scenario, and 50% of time we're in the second scenario. Then we put a plus sign to add this up together. And this addition in quantum physics we call it superposition. So these two quantum states are superimposed on another. That means 50% of the time we're measuring the quantum states in the first is according to the first term. And 50% of the time, the quantum states of these two particles in the second term. So that's what it means. Let's now assume that we do have two pair of particles that share these quantum states. However, what is striking and is surprising to the physicists at the time is that this kind of quantum states will lead to a very unusual consequence. And that consequence is that suppose this one person is trying to make an observation on the first particle, measuring whether it's a spin up or spin down. And the moment that observation is made, instantaneously, the second particle will be in the opposite states. So this is as if there's some hidden actions that when you try to perform on the first particle, and there's some hidden action that's actually determining instantaneously the state of the second particles. Right? And this happens not only when these two particles are close together. Actually, if we separate these two particles to a very large distance, for example, the first electron spin is somewhere in Chicago, where I'm located in right now, and the other particle is in New Mexico cities, and so that's where you are at. Now, if we want to perform the same experiments, we'll see the same bizarre phenomena where my observation was instantaneously determining the state of your particle in the Mexico City. Right? So that sounds very strange, and it's very confusing also at the same time. And if you feel confused, don't worry, and you are not alone. Actually, you are in good league with some of the greatest scientists in the 20th century or ever on Earth. Albert Einstein is one of them who actually don't believe these spooky actions at distance actually can happen. So in one of his famous quotes, he actually seriously disbelieved in the quantum mechanics, and he called this bizarre phenomenon the spooky actions at the distance. Now, in the year of 1935, Albert Einstein, along with other two famous physicists at that time, Podolsky and Rosen, they together write a very famous paper, and which questions about the correctness of quantum mechanics. And the title of this paper is called "Can Quantum Mechanical Description of Physical Reality Be Considered Complete?" Now, ever since then, the entire community of physics start to have a heated debate about the quantum physics, and especially around this bizarre concept of quantum entanglement. And this dispute remained for many, many decades to come. Until the year of 1964, another physicist or mathematician called John Bell come to a brilliant proposals. So John Bell, he devised this new theorem, which now we call the Bell theorem. Now I'm going to present to you this theorem, not in a mathematical form, but I will describe it in terms of a game. Now, how to play this game? There are two parties of the game, Alice and Bob. And the game is played such that first, Alice and Bob each will receive a pair of photons and generated by some third parties. And these photons are going to be in a quantum state, so we can say it's entangled states. And their job is to make measurements individually or independently on one part of these photons they received. So Alice will receive one photon from this pair, and Bob will receive another photon from these pairs. Now, upon receiving these particles, what they're going to do is they're going to decide to make some observations or making a setting to measure these particles. And there are two possible settings. Here we say this 1 and 2, there's two possible settings. Once they decide on the measurement settings, they can measure two possible outcomes. So using an example of electron spins as this quantum particle, one possible setting would be measuring the orientation of these spins along the vertical directions. Right? So that's what we call the one possible settings. And the two possible outcomes are the ones that either spin is pointing positive up or spin up or spin down. So that's give you an example of how possibly they can measure the particle along different settings and obtain two different possible outcomes. And these two possible outcomes assign two different values. One is 1 and the other one is -1. Okay, now Alice and Bob enter this game, both Alice and Bob, and receive some particles, and they're going to perform independent measurement on them. So after many, many trials, many, many rounds of these experiments or these games, they come together and combine their measurement outcomes to compute a single parameter according to the following formula. This is the second formula I'm going to show you. And the outcome of that formula gives a parameter called S parameter. So let's not to be bothered about how to perform this mathematics. Let's say this is a very simple step. Combine the result together, you can compute this S value. Now the rule of the game says is this S value is greater than 2, Alice and Bob can win these games. They collectively win these games. And later they find out that the Bell theory states the only chance that Alice and Bob can win this game is that initially these two particles are in this shared entangled states. And in other words, the only chance that Alice and Bob can win this game is that the quantum entanglement is real and the spooky actions is actually happening. If not, no matter how hard they tried, Alice and Bob will never win this game because the Bell theory states that for any unentangled particles, this S parameter will be always less than the value of 2. Okay, so this is my version of description of the Bell's theorem in terms of a game. And after the proposal of this Bell theorem, as you can imagine, scientists around the globe are in a race to implement or realize these experiments to test whether the quantum entanglement is real or not. Now, the time comes to nearly 8 decades later, and that was last year, 2022. This is a year of celebration for quantum physics, especially for quantum entanglement, because 3 of the experimentalists, Alan Nesbitt, John Clauser, and Anton Zeilinger, they independently contribute to a successful experiment that prove or disapprove the Bell's theorem. So in other words, they independently did some experiments, and the common ingredient of the experiments is what we call entangled photons. And they were able to establish the violation of the Bell inequalities, and therefore giving a pioneering contribution in quantum information science. Okay, so what exactly do they do? How do they realize the experiments? Now let me walk you through very quickly some of the key ingredients, how to make these experiments happen. So to make the Bell's games happen, what we need first is an apparatus that can generate entangled particles. And in this example, people now typically use photons as their entangled particles. Now, what is a photon? Briefly speaking, photon is the particles, the smallest building block of light. Right? So you can imagine that the light consists of many strings of these tiny particles, which we call them photons. Now, there is a special material called optical nonlinear crystals, indicated by this square box, yellow box. When you shine a strong laser light onto these crystals, very occasionally, this crystal can do the magic that split these input photons into two lower energy photons. So it's like a fission process. This one high energy photon, sometimes they split up into two daughter photons, which we usually call them as signal and idler photons. So these are photons that come in always in pairs. They're created in pairs. And the whole process obeys the usual energy and momentum conservation, such that the sum of the momentum of two photons adds up to the momentum of the input laser photons. And energy of these photon pairs add up to the energy of the input photon as well. But thankfully, fortunately or unfortunately, because of this process is so inefficient, it rarely happens. So basically, for every billion of input photons, only one pair of photons are created. This is how inefficient it is. But whenever that happens, there's some really magical things that's occurring, because now these two photons are correlated with each other. Now, they are correlated not only in energy, because we say the sum of these two photons are fixed, but individual photons' energy are not fixed. They're allowed to have some room to wiggle. These two photons are also correlated in time, because they always come up, they're created together. Right? So they are not created independent of each other. If one is created, you know the other one is also created. And third, they're also created in so-called polarization. So polarization of photon has the same meaning of polarization of light wave. So we all know that light can oscillate in different orientations. For linear polarized light, there are two orientations, for example, horizontally polarized light or vertically polarized light. So single photon has the same property of polarizations. And this pair of photons, they usually have opposite polarizations, meaning if one photon is horizontally polarized, the other one has to be vertically polarized, and vice versa. Now, with these ingredients of entangled photons, now we can create something called polarization entangled states, or Bell states. And how do people do that? They take this crystal, and now you imagine we can take a camera, make a picture at the back of this crystal. What you will see is actually the light, all possible orientations of the light propagation directions will trace out to two rings. Why there are two rings? Because there are two photons. One is slightly tilted up, that makes up the upper ring, and the other photon is always tilting down, like the lower ring. And these two rings represent photons of always opposite polarization. So let's say the top rings represent photons with a vertical polarization, meaning the electric field of that photon is always oscillating vertically. And the lower ring represent the photons always horizontal polarizations. Now these two rings are intercepting each other at two particular points. Right? There's a two intersection point. We say the left intersection and then the right intersections. What is interesting about this picture is that what happens at these two rings? Suppose that we detect a pair of photons on these two positions, to these interception points. There are two possible scenarios, right? Because first of all, the first scenario is that the photons arriving on the left intersection is a horizontal polarized photon. So we write it as HL. And when that happens, the photon, there's guaranteed to be another photon because photons come in pairs that is vertically polarized, that happening, emerging out of the left intersection point. So this is HV photons is a one scenario when we get a two photon detected out of these two intersection points. However, there's another possibility because this is an intersection. The first photon actually can come out of the top ring, which is the vertical photons. So you have a vertical photon on the left and the horizontal photon on the right. This is another possibility. Now, since we can't distinguish which case it is when we detect two photons, what we do is we add them up, like the case I'm showing you in the first slides. We superimpose these two possibilities, and mathematically we put a plus sign to combine these two quantum states. And the result of that is this entangled states, right? Actually, I show you in the previous slides is the HV plus VH. Now we're using the polarization state of two photons to encode these quantum states, but this quantum state indicates no matter which state of we're measuring the first photons, the second photon always have the opposite polarizations, and that's what this state means. And it turns out John Bell defined this as a Bell states. And this is not only this is actually not the only Bell states. There are total of 4 possible Bell states, which I'll show you later on in these lectures. Now we have the source. The next thing we need to figure out a way to make measurements. What does it mean to make observation on those entangled photons? To do so, we actually can use something very common in our daily life, which is basically a sunglass. Right? Your sunglass that we're wearing every day, usually during the summer days, it consists of a piece of glass that we call polarizers. This polarizer has a particular axis or direction where if the polarization of light is along that direction, that photon can pass through that polarizer or sunglasses. And if the polarization is perpendicular to that axis, then this polarizer will block that photons. So now we can have two polarizers that place in front of the detectors into the beam of these entangled photons. By rotating these polarization angles, we can tell the polarization state of the photons. If both photons can pass through these two polarizers, they'll make it to the detectors and they make a click. And whenever we receive 2 clicks, we call it coincidence. Okay. And the possible ways to measure the polarization are not only along the H and the V axis. Actually, we can rotate this axis at any angle in between. One example is if we rotate 45 degrees from the horizontal and vertical, then we're effectively measuring the photons along the so-called diagonal or D and anti-diagonal basis. So A and D basis is another possible basis for measuring the photons of entangled pairs. So here is just a very, very quick exercise just to illustrate the point. I don't expect everyone to work through this mathematics together with me, but I just want to show an example. If you're given a entangled states like this, H and V plus VH, and if we set the polarization angles, polarizer angles, one to be H and the other in V, then 50% of time, we can get 2 of the photons transmitted through these 2 polarizers. And that's why we call it a coincidence. And the reason why we can only get 50% of the time is because only the first term, the photons represented by the first term can pass through these 2 polarizers, or the second cannot. Now, I won't go through the rest of the list, but basically, you can leave it as an exercise to convince yourself. By setting up the polarizer at different angles, you get different possibility of 2 photon clicks. And in fact, people have done experiments on this pair of photons. If they plot the probability or coincidence when 2 photons also pass through the polarizer as a function of the angle, as you continuously tune the angle of the polarizers, they will trace out this very interesting sinusoidal pattern, which looks like an interference pattern when we learn about optics or how light interferes with each other. In fact, this is exactly the signature of a quantum entanglement, where the plot we will show is called 2 photon interference. Now let's combine these ingredients together and reiterate how we realize this Bell's game theory. So first of all, we start with generating a source in the middle that generating string of the entangled photons. One is sending to Alice, one is sending to Bob. And Alice and Bob will first make a choice of which basis they want to measure. So in this case, we made the example of either using HV basis or diagonal, anti-diagonal basis to measure the polarization of the photons. And whenever they settle down on one set of settings, there are always 2 possible outcomes, let's say the H or V, A or D, and the signed values plus and 1 to those possible outcomes. Now, after many, many rounds of the experiments, they repeat these experiments many, many times. After that, they combine their results together and plug in this formula that I showed you earlier to compute S parameter. Right? For those who are experts in the audience, this formula basically means, let's say the first term means they take the product of the outcome obtained by Alice and Bob. So these are a bunch of +1s and -1s, and take the product of the 2 corresponding to the 2 bases they're chosen to measure the pair of photons. And since there are many, many instances, because they repeat the measurement many times, each term represents an average value of those measurements. So combined together, they compute this S parameter. And if this S value is greater than 2, they know for sure that these 2 particles they start measuring is indeed in this quantum entangled states. And therefore, the Bell inequality is violated. So that's the summary of the Bell theory. Now, this looks easy, but it's much harder to really implement these experiments. It took about the scientists around the world about another 4 decades until they actually realized successfully these experiments. So in the year of 2015, which is a really great year for John Bell, and arguably not so great year for Albert Einstein, the 3 independent research groups in Netherlands, Vienna, and the United States, they perform independent experiments, and all of that give a conclusive results of the Bell inequality, and which means they either falsify the theorem of quantum entanglement or prove that quantum entanglement is real. Now, of course, as we now know that the end result is that all of these 3 groups, they successfully shown the S parameter that's greater than 2, meaning they prove that quantum entanglement, it is indeed happening. Now, just merely 2 years later, another group of scientists from China actually extended these experiments to much, much bigger scales. They launched a satellite and putting this entangled photon source onto the satellite, meaning the satellite is generating a pair of entangled photons, and these 2 photons are beamed down onto 2 telescopes that are located on the ground. And the physical separation of these 2 telescopes about 1,200 kilometers. So this is a really grand scale experiments. And no surprise, when they compute the results of the S parameters, it again violates the Bell inequality, showing S parameter at greater than 2, and proves that this spooky actions at distance is actually a real thing. Now, that's a very quick history, review of the history about the development and our involving understanding of quantum physics, especially about this bizarre phenomenon of quantum entanglement. Now, ever since the confirmation of the quantum entanglement, the next natural question is whether we can utilize this physical principle for useful applications in real life. As it turned out, there are indeed multitudes of applications that can take advantage of quantum entanglement and make benefit to our daily lives. Here I'm going to show you two simple examples, how the quantum entanglement can help to enhance either the security or the speed of communications. Now, the first example I would like to give you is about quantum cryptography. Now, before we look at the quantum cryptography, we would like to discuss how the classical cryptography is done today. Right? So this is something that we're using every day in our daily life. Whenever we enter a password, log into our account, there's always some cryptography that's happening behind the scenes, the encrypting and decrypting. And the technology we use today, which is the classical technology, is called one-time pad or private key cryptography technology. The way it works is like if Alice wants to send some secret message to Bob, she wants to first encrypt her message, and then her message is presented by this string of random 0 and 1s in the binary format. She also in possession of this random string, which she called key. This key is shared between Alice and Bob and only to them, and meaning no third party has knowledge of these keys. The Alice performs a binary sum of the message she wants to send and these keys. And the binary sum works like if the bits are different, they end up being 1. If the bits are the same, always is 0. So after this binary sum, what they get is an encrypted, Alice gets is encrypted message. And this encrypted message is sent to Bob over a standard communication channel, for example, internet. Now, upon receiving this encrypted message, Bob, since Bob has the same keys, she will perform a binary sum of the key strings and the encrypted message. And very surprisingly, this operation will recover completely the original message that Alice wants to send. So this is the way that the cryptography is done today, and then this is the way that ensures the secrecy of the Alice, the message to Bob. And as we can see, the secrecy or how secure this message is really relies on the fact that both Alice and Bob can start sharing these identical bit strings, which they called private keys. And these keys, pair of keys, are only known to them, but without known to any third parties. Now, the question is, can quantum mechanics, or specifically quantum entanglement, help to generate these keys to Alice and Bob without the third party knowing it? And the answer is yes. And there's a specific technology which we call quantum key distributions, or QKDs, are going to do exactly that. So here is how it works. First, we start preparing entangled states of two photons. Let's say, for example, for illustrative example, this state is HH plus VV, meaning this polarization state of two photons always identical to each other. Now, these two photons are one sent to Alice, one sent to Bob. Upon receiving these two photons, Alice and Bob will first decide which basis to measure them. As again, it's either, for example, it's either HV and AD basis. And upon deciding on the measurement basis, there are always two possible outcomes. And then they can randomly assign 0 or 1s to each of the possible outcomes. So after repeating this measurement many, many times, they receive lots of photons, then measuring on them. They each accumulate these measurement records, right? So they write down the basis they choose to measure, and they write down the value they measure. So after many rounds of measurement, they stop and start to announcing to each other what are the measurement bases they chose to do this measurement. And what they decide is that if their measurement bases agree with each other, let's say both of them choose HV and HV basis, they call it a good record and they keep the result of the record. On the other hand, if the bases differ from each other, they say it's a bad record and delete that record. So after compiling this long list they come up with the bit streams. For example, in this case, Alice will get a bit stream that start with 0, 1, 0. Likewise, Bob also gets bit stream of 0, 1, 0. So now they have a random shared bit streams. Now they can use as a keys. And the fact that they can always guarantee to get the same bit streams is because of the entanglement. This entangled state guarantees whatever Alice measured and Bob will measure the same value if the bases agree with each other. Right? So now some of you may wonder why this is secure. What happens if there's an eavesdropper? Can this still happen with no leakage of information? Let's suppose there are some eavesdropper, third party, want to intercept these photons before it transmitted to Alice or Bob. In quantum physics, there's another theory that says if you are measuring, someone is measuring on the quantum states or making observation of the quantum states, it necessarily has to correct that quantum states. So if the eavesdropper is present, she wants to make a measurement on this quantum entangled states, and that necessarily will correct this entanglement. So for Alice and Bob, then what they can do is to use the Bell inequality or Bell test to test whether this entanglement is still intact or not. So the protocol basically follows Alice and Bob perform this Bell test measurement, measuring their photons, and they later compare the statistics and compute S parameter. If they find that S parameter is no longer greater than 2, then they knew that someone is measuring on the entanglement, and therefore the communication is no longer secure. So this is one way that quantum mechanics can always guarantee that the communication is not hacked. And that's how quantum physics, quantum entanglement can enable ultimately secure, unhackable communications. So that's one example about QKD and then quantum cryptography. Another famous example is teleportation. I don't know about you. I'm sure some of you, when I heard the word about teleportation, this is the first picture come to mind, right? Unfortunately, the teleportation I'm going to discuss about is not this Star Trek-like teleportation, but it's more of a kind of a information theoretic teleportation where we try to transfer information, quantum information, from one place to another place, seemingly instantaneously. Okay, so let's formalize that statement. Quantum teleportation refers to a process where one party, Alice, transfer an unknown quantum state or arbitrary quantum states, which is a superposition between a H states and the V states, or in quantum computing language, this is a superposition between 0 and 1s. Let's say if H is representing 0 and V representing 1. And alpha beta are arbitrary complex numbers that describe the probability or weight between these two states. Now, Alice wants to transfer this quantum state to Bob using only one pair of entangled particles and some classical communications. And this task is not going to be possible to be performed with only classical methods, because a simple argument is that for alpha and beta, this coefficient in front of the 0 and the 1s, they can be complex numbers. To represent the complex numbers will consume infinite number of classical bits, right? Because imagine it's an irrational number. To precisely represent that number, you need infinite bit streams to do so. So let alone to transmit that infinite information over a communication. So this is not actually a doable task for any classical technologies. Now let's see how can we do it with quantum entanglement. The protocol follows where we need the 3 particles. The particle 1 to represent the quantum state, we want to teleport, and the particle 2 and particle 3 are entangled pairs. The first step of the protocol is that first we'll have to distribute these entangled particles. In this case, we use example of entangled photons. The photons 2 and photon number 2 and the number 3 are first distributed to Alice and Bob. These are the 2 people who want to perform the teleportation. Again, let's assume that this entangled states in this HV plus VH states. Now, second step of this teleportation is that Alice will combine the first photon and the second photon to make a joint measurement. Now, what do I mean by joint measurement? Is to determine the collective quantum states of these two particles, particle number 1, particle number 2. And there are altogether all possible outcomes, which corresponds to 4 possible Bell states. So Alice can only measure one of the 4 possibilities of this joint measurements. So for the argument's sake, let's say the measurement outcome of Alice measurement on photon 1 and photon 2 is this H and V plus VH states. And mathematically, we can, again, this is for those audience who are expert in mathematics, we can first write the collective quantum states between the 3 particles, number 1, number 2, and 3. And just by simply rearranging the terms, by combining the state of the first particle and the second particle into this state where Alice measures, that automatically projects this quantum state of the third photon that Bob receives into this initial states that Alice wants to teleport. So that's the third step of the teleportation. And Alice announces this measurement results to Bob through a classical channel. Upon receiving these photons by Bob and the signal, the information that Alice announces to Bob, which measurement outcomes, and Bob can do some local performance that turn the third photon that he receives into this exact number 1 photons where Alice wants to teleport. In this particular case, actually Bob doesn't need to do anything because the state that coming to him is already the state that Alice wants to teleport. And in this case, a teleportation is complete and the arbitrary quantum states at the beginning is completely transferred to Bob. And this happens without actual communication. Notice that Alice didn't say anything about this quantum states to Bob. All she tells Bob is one of these 4 possible outcomes, measurement outcomes of the joint state of 2 photons. So as I promised, I only use the example of the first case where we show this one only specific Bell states, and that gives a Bob the exact state where Alice wants to teleport. But also there are other 3 possibilities which correspond to 2, altogether the 4 possible Bell states. So this is number 2, 3, and 4 are the possible states that Alice can measure. And upon receiving the photons by Bob, Bob only needs to do some simple local operations. In this case, simply rotating his polarizers, he can recover the initial quantum states that Alice wants to teleport. Okay, I know that sounds a little bit abstract, but actually people have been very successful in realizing this kind of experiments. In this example of a landmark experiment, a group of scientists from Vienna actually done these experiments over 2 islands. There's Tenerife Islands and La Palma Islands in Spain. These 2 islands are separated by 143 kilometers. And they're performing this experiment using the 2 telescopes on top of their observatories at the peak of these 2 islands. Here, I'm going to skip the details, but basically they were able to show that a arbitrary quantum states representing photons is transmitted over 140 kilometers successfully. Not only people can do these experiments in open space, in remote environments, they actually can do this in the metropolitan settings. So this experiment in 2016 is done in Calgary City in Canada, where they teleported successfully a photonic quantum states over a distance of 6.2 kilometers in the downtown area. And in this case, instead of sending photons through air, they actually send photons through optical fibers that's laid underground, which allows a very efficient transfer of photons. The photon can travel through this optical fibers, there's very minimal loss. Okay, here are the details of experiments, but you don't have to bother about that. Eventually, this experiment is also successful in showing that an arbitrary quantum state can be transferred. All right, so I think my time is close to the end. So I would like to use maybe the last few minutes I have to give you a very, very quick update of what is actually going on around the world right now in the laboratories, in the startup companies. People are in a race to build this first realization for quantum network. So in the example I just showed you, the QKD and interpretation, people have been already showing that some sort of a communication can happen over a relatively short distance, and which we call metropolitan scales on the order of 10 to 50 kilometers. And today you can buy commercial products actually can deliver this quantum encrypted keys with communication bandwidth up to about 10 megabits per second, which is already great. That means we can literally having this Zoom calls using quantum technologies. However, the grand goal of the quantum network is able to not only send this information over a city scale, but we do want to communicate with our family and friends over the globe, like intercontinentally. But there is a problem. The problem is that if you try to send these photons over the traditional optical fibers, the chance that you can receive that photon at the other end of the fiber decreases drastically with increasing length of this fiber. For example, if this fiber is going to be 1,000 kilometers, the chance you can receive one photon successfully at the end of the other end of the fiber is something like once in 300 years, which means it's completely impractical, and this type of communication over long distance will not happen. So to overcome this issue, and people have come up with a very interesting solution. So instead of sending photons directly over a very long distance, how about we make the photons having pit stops in the middle, and the distance between these pit stops are small enough that there's a high chance the photon can transmit it through. So that's the quantum repeater-based quantum network. Another solution is utilizing satellite, because the satellite is orbiting the Earth roughly one round per couple of hours, can carry the entanglement over very large distances. And whenever we need it, we can send the information down from the satellite to the ground station, or beam it up from the ground station to the satellite. And the distance between the satellite and the ground station is not very long. It's about 20 to 30 miles, which means we can do the photon transmission relatively efficiently. Now, among these two possible solutions, I think the more mainstream techniques is building this quantum repeater-based quantum network. Again, the general strategy is that you break up this long quantum link into a shorter distance links, and first try to create entanglements among the shorter distance links, and gradually grow this link to a bigger one. So the only requirements for making this quantum repeater network is we need something that can store the photon information that's carried by the photons. And this device is what we call the quantum memories. And depends on how big is the network, there's a different requirements on the storage time, so how long this quantum memory needs to store information. For example, if the quantum network is about 1,000 kilometers long, then we'll need quantum memory at least capable of storing quantum information for about 5 milliseconds. So then there are many groups of researchers around the world are trying to build these quantum memories. And the first proposal is based on individual atoms. You can trap these atoms using lasers inside optical cavities between the two mirrors. And it turns out the internal energy levels of these atoms can be used to generate photons and also serve as a quantum memory. Another class of materials that people are researching actively is based on atoms that trap inside the solids or inside materials. Some notable examples are like color centers or defects in diamonds. The reason why diamond is so shiny is because they're actually not that pure. it consists of a lot of defects within the diamonds. And these defects, as scientists later find out, are really great candidate for quantum memories to storing the information in the quantum light. There are other technologies such as missing atoms in semiconductor materials, or myself are interested in this very specific class of atoms called rare earth atoms. They both, all of them can serve as a photon, a atom that generating photons, but also it has the ability to store quantum information into the memories. So this is my final slides. I think as of today, there are a lot of scientists around the globe and trying to create their own version of the quantum network in Asia, in China, in Europe, and also there's many groups in the United States building their own versions. And we also have a little bit of the test beds here at the Chicago metropolitan area. My hope today is that my lecture hopefully will inspire many of you to be interested in these very exciting new technologies. And someday we hope that in the near future, we can start enjoying the benefits bring forth by the quantum technologies. So with that, thank you very much. I hope to have a bit more time to answer the questions that you may have. So with that, thank you for your attention.
Thank you very much, Dr. Tian. Yeah, we have some questions. First of all, thank you for your lecture. It is very interesting and it has awakened the interest in all our audience. So I'm going to read for you some of the questions we have received until now, and if comes more, I will ask you if you are okay in answering them all, okay? Yeah. Okay. The first one is it possible to theoretically describe what happens inside the VVO crystal?
Yes, so today I think we have really gained lots of deep understanding of this. These slides will show you the so-called spontaneous parametric down conversion process, where the down conversion itself can be described very precisely mathematically as a Hamiltonian. And the photon creation process can also be modeled and simulated and to be predicted to a very great precision today. So it is indeed a very doable task right now. It was not so maybe 20 years ago, but I think it's almost becoming a routine. Like in my lab, we have a BBO crystals that are generating these entangled photons almost daily.
Thank you very much. Next question is, how can we measure the rate of entanglement of the two output photons?
So the degree of entanglement, I assume that's the question?
Yeah, the rate of entanglement, yeah, or the degree of entanglement.
Yeah, so as I can, if I can recap, so we utilize this Bell inequality formula to construct this particular S parameter. I don't know if actually it's probably easier just to go back to that slice. So the degree of entanglement is actually all captured by this S parameter. A perfect entangled states, or we call it maximally entangled states, will give a S parameter that reaching an extreme value of 2 square root of 2. If your entanglement is not perfect, then your S parameter will be somewhere in between value of 2 and 2 square root of 2. So depends on where it is in that range, you can tell how the degree of your entanglement. Yeah, that's a very excellent question.
Perfect. Next one, it's from our audience. I am intrigued that only 2 transmission possibilities are involved with quantum internet via fiber optics and satellites. What about electromagnetic waves and 5 gigahertz and 6 gigahertz? Is it possible to send quantum internet over these frequencies?
You know, that's a brilliant and excellent question. You know, myself have similar thoughts before. But I mean, I still don't want to dismiss the possibility using the wireless, ENM waves in the microwave range to transmit entangled signals. I personally still think it's possible, but there's one obvious challenge in that is because when you do wireless transmission, the signal is encoded in the form of either radio frequency or microwave electromagnetic waves. So, and the microwave signals happening at the 5 gigahertz has actually a very small energies. So these are correspondingly the milli-eV energy scales compared to EVs for electron volts for the optical photons. And at ambient environments, because the ambient is about 300 Kelvin, right? So the thermal energy from the environment is already bigger than this photon energy of the microwave. So in other words, if you try to do a quantum communication using microwave photons, you are subject to all the thermal noise in the environment. And very quickly, I think your quantum signal will be swamped by the background noise, just simply because of the temperature of the ambient. But
Thank you very much.
A very thought-provoking question. We wish we can explore that idea further together.
Okay. Well, we have many questions, so you can tell me until what point you want to stop. Okay, Dr. Tian.
All right. Yeah. Let's keep going unless Boris, you have a clear cutoff time.
Okay. Next question. There exists any equivalent to protocols IPv4 or IPv6 inside quantum internet?
Yes, there's some established protocols for quantum internet that is similar to the BB84. Examples are Barry-Koch protocol, the DLCZ protocol is another very famous one, which followed, named after 4 individual scientists. So DLCZ, these are 4 people's initials, and it's actually remains an active research area. People are still looking into newer and protocols to for quantum network.
Thank you very much. Next one. Talking about experiments, the yellow box in a non-linear optical material, but what specific characteristic has to split the photon and measure the Bell inequality S?
What's the specific task?
Let me see. Well, this is from Jessica Huelgas. If you want to open your microphone, we can give you the privilege. Let me see. I will send you an invitation to start your microphone if you want to propose your question directly. And in the meantime, we have another one. Which range of frequencies, energies, or color are the photons used for these experiments of entanglement?
Yeah, so for the experiments that showing in these slides, the entangled photons typically has the wavelengths in the visible range, meaning something in the range of 400 nanometer to 700 nanometers. And there are many variety of different versions. So typically is around 400 nanometers. So it's a blue photon. If you're very sensitive to eyes can see it, it will be a blue color.
Thank you so much. Next one. In your opinion, what technology in materials is most reliable to create qubits?
Okay, yeah, that's a good question, but I'm not sure I'm confident to give you a very specific answer. I would say is that I would like to say that currently there are many different material platforms are being investigated by different research groups. Some of them are superconducting materials, like based on superconductors. Some of them are based on semiconductors, like electron spins in silicon. Some of them are a combination of both. It's a hybrid between the semiconductor and the superconductor. And some of them are purely just photons. They are not actual materials, but it's optical waves. Use that and encode qubits. So I don't think there's a clear winner at the moment. So different platforms have its own advantage and disadvantages, and they may be suited for different aspects of quantum computing. But so far, I couldn't pinpoint a clear winner yet.
Thank you very much. Jessica has already answered. I am asking you to mute, so go ahead, Jessica. You have to receive, okay, there you are.
Oh, thank you very much. Well, I would like to know about it, talking about the experiments.
Yeah.
The yellow box is a nonlinear optical material.
Yes.
But what specific characteristics has to split the photons and to measure the Bell inequality as?
I see. Yeah, thanks for that question. So I didn't have the time to explain all that detailed properties, but this type of crystals is special in the sense that it can respond to light in a way that's nonlinear. Nonlinear means the output from these crystals will have a different frequency than its input photons. So this nonlinearity typically happens in a material where these electrons are very tightly bound to the nucleus of the atoms, such that when you shine strong lasers on them, this laser is going to drive the electrons orbiting the nucleus into a highly excited state. When the excited states become so high, then they start to distort. And when this atom come back to the ground states, will emit a photon that's different in wavelengths, in frequency, than the original photons. That's why we call these crystals nonlinear crystals, because their response is nonlinear. So that's nonlinearity is the one that gives rise to the creation of the photon pairs, because the photons that produced by this down conversion process will have a different frequency or energy than the initial photons. So that's the characteristics of this type of crystals.
Thank you so much. We have 3, 5, 6 to go.
Right.
Okay.
Oh.
You let me know. Okay, Tian. Okay, next one. So potentially we could make an instantaneous transmission of information from one planet to another?
Thanks very much for that question. Yes, I would say, other than the words instantaneous, yes, this is indeed true. So the spooky actions at distance, as the way they explain it, sounded like this information is actually instantaneously transferred, and then this transfer is happening faster than speed of light. But in actual fact, if you want to do this quantum transfer, the measurement, we're still making a measurement locally and to tell the other party what's the measurement outcomes. The measurement results has to be transmitted at fastest the speed of light. The fastest possible speed is still speed of light. So I do not believe that this information transfer are happening at the speed faster than speed of light. So it's not a superluminal information transfer. It's not instantaneous, but indeed it can happen over very arbitrary large distance, for example, across the different planets.
Okay. Next one. Is there any experiment that can be performed in a quantum computer of few qubits in order to gain experience and start working in these topics?
Oh yeah, excellent. So even though my lecture today didn't touch much about quantum computing, I'm only focused on the quantum communication. Today, indeed, you will have the opportunity to utilizing some commercially offered quantum computers, for example, the one offered by IBM. the public available version of it consists of 5 qubits. And you can subscribe an account with IBM Quantum, and then you can start programming that quantum computer to do a 5 qubits algorithms. And there's already many interesting algorithms out there, and you are definitely encouraged to give it a try. It's a lot of fun.
Okay, thank you very much. Questions keep coming and coming. I will give you until what about 5 minutes more?
All right, yeah.
Those who are not answered, I will send them by email. Do you agree?
All right, yeah, absolutely. Thank you.
Okay, next one. Next one is very long. It says, returning to the quantum information transmission protocols, you talked about one where Alice prepares her qubits in one basis, and later she tells Bob what basis she used in order for him to measure the qubit in the right basis to obtain the information of the qubit. If one thinks about it, the only thing that prohibits quantum information to travel faster than speed of light is the fact that Alice announces Bob through a classical channel the basis that she used. But if she didn't do that, and Bob had to choose randomly a basis, there exists 4 of them, for what I understood, isn't there 1/4 chances that he chooses the right basis and therefore that information travel faster than light? Thank you. That's the question.
Yeah, again, excellent question. And I agree everything that's commented in that question. Because of the need to do classical communication, there's no faster than speed of light information transfer in the protocol we just described. And in the likely scenario where Bob happened to measure in the same basis, let's say before he even received this basis choice from Alice, Bob somehow chose to measure a certain basis, and that basis turns out to be correct. Whether the results that Bob measured indicate there's a instantaneous information transfer. All right, so my answer is still no, because without knowing Alice, the measurement basis announcements, there's no way for Bob to know whether the measurement outcome that Bob obtains is correlated with Alice's measurement. In other words, Bob can make a measurement before Alice's measurement results comes, but at that time, Bob will have no information about whether the state of his quantum states. And at that point, that measurement is meaningless because there's no reference. The information only become meaningful when it's compared with Alice, the measurement. That correlation is the one that gives the information.
Thank you very much. Well, we have run out of time. We want to thank you for your very interesting lecture. As you can see, with a number of questions that have arisen, that this topic is awakening our interest. So thank you so much, Dr. Tian. All questions that are still waiting for an answer, I will send them you by email. And I give the word to Dr. Boris to give us just the farewell.
Thanks very much.
Thank you very much. Can you hear me well, Tian?
Yes, I can hear you.
Okay. It's been a marvelous conference. As you see from the questions, people are really excited about this talk, and it has really triggered many questions, interesting questions, as you can see. So I can I want to thank you really for this conference. It's been very enlightening for us, and I'm sure that it has been inspirational for many people who want to study this further. So thank you very much on behalf of everyone here. Tian Zhong, I hope we meet again soon. Thank you very much.
Yeah, thanks, Boris, for this marvelous opportunity. It's also my great pleasure to be here and give this lecture. I hope to have the chance to interact with you again soon in the future.
Great, thank you. Thank you very much, everyone, for attending the conference.
Bye.
Bye. See you, everyone. tomorrow's morning. Bye-bye.